Hey guys, welcome to class. Today we are going to do lesson 4.1 where we take a look at factors and prime factorization. So before we jump into prime factorization, we need to review a couple vocab words that you've probably heard before, and that is what a prime number and a composite number are. So a prime number is a whole number greater than 1. So we're looking at just positive numbers right now. And it has exactly 2 whole number factors, one in itself. So for example, the number 7 would be a prime number because the only factors to 7 are 1 and 7. 13 would also be a prime number because the only factors, the only numbers that 13 can divide by are 1 and itself 13. Any number that is not a prime number is called a composite number, which is a whole number greater than 1 that has more than 2 factors. So if it has exactly 2 factors, it's a prime number. If it has more than 2 factors, it's called a composite number. And the prime factorization then is when you write a number as the product of its primes. Now that word product should jump out to you. We've talked about it before. It means multiplication. So it means when we are going to write it as the multiplication of the prime numbers that make it up. And we'll get into prime factorization in just a second here. So take just a minute and get these vocab words written down. You can pause the video if you need more time to write the definitions. All right, so this next chart here is actually not in your notes, so you can put your pen or stylus down for just a minute because I want you to look on the board as we follow along here. All right, so when we talk about numbers, any number, and we are trying to identify if they're prime or composite, we talk about their factors. Now, I need you to understand there's a difference between listing a number's factors and a number's prime factorization. Okay, so we're going to start with just all of the factors. So for example, if I ask you to list the factors of 24, it has quite a few. We try to write them in order from least to greatest. So this would be 1, 2, 3, 4, 6, 8, 12, and 24. Those are all of the numbers that can divide evenly into 24. And perhaps maybe when you've seen this before, sometimes we call this a factor rainbow because obviously factors come in pairs. So like 1 and 24, 2 and 12, 3 and 8, and 4 and 6 are the pairs that multiply to 24. But again, when we list factors, we like to list those in order from least to greatest. And so obviously because 24 has way more than 2 factors, we know that it would be a composite number. All right, then as we look at 41, well, as we try to think through the factors of 41, we figure out pretty quickly that 41 only has 2 factors, 1 in itself. There's no other number that divides into 41, and so 41 would be a prime number. 51 is one that kind of tricks people. If you remember, we talked about how the trick to figure out if a number is divisible by 3 is you add its digits. And so when you add there, you do see that 51 is divisible by 3. So 51 is one that people always think is prime, but it's actually not because the factors are 1, 3, 17, and 51. And so this would be a composite number. The next one's 1. 1 is actually the only number that is neither prime nor composite because prime has to have exactly 2 factors, composite has more than 2 factors, and 1 has 1 factor. So this is the only one that is neither prime nor composite because it only has 1 factor, 1. Okay, so hopefully you get the idea here. Again, this isn't in your notes, but I just wanted to make sure you understood that when we ask for all of the factors, we are listing all of those factors in order from least to greatest. And that's different than the prime factorization. Okay, so all of the factors would be every single number that divides into it. Now we're going to go into prime factorization. Okay, so when we talk about a number's prime factorization, that is something that identifies the number. So it's important to know that every number only has exactly one prime factorization, and every prime factorization pairs to exactly one number. Okay, it's sort of like if you're aware, like you have a social security number, and every United States citizen has a social security number. That social security number identifies you. You have one social security number, and you are the only person in the world that or in the country that has that social security number. Okay, so it helps identify you. The same is true for prime factorization. The number 630, for example, has exactly one prime factorization, and that prime factorization pairs only to 630. Okay, so we talked about how prime factorization is the product, the multiplication of its prime factors. So not all of its factors, only its prime factors. And the easiest way to find that is with a factor tree. All right, there are other ways to find the prime factorization as well, and if you used a different way in the past, you're welcome to continue using that way as long as you show your work. But I personally think factor trees are one of the easiest ways to go. So let's start with 630, and what we're going to do is we need to pick two pairs of numbers that are factors of 630, two numbers that multiply to 630. So there's lots of things you could choose from. I'm going to start with 63 and 10. Now, if you're thinking, that's not what I started with, just hold your thought for just a second, because there is more than one way to do this, and we'll talk about that in just a moment. Okay, so 63 and 10, then 63, I'm going to break into its factors, which would be 9 and 7. And whenever you hit a prime number, you are going to circle it. So 7 can't break down any further, so I'm going to circle it because that quote-unquote branch is done. 9 can keep breaking down further to 3 and 3, and 3 is prime, so I'm going to circle both of those so that branch is done. Then I'm going to come over to 10, and 10 can break into 2 and 5, but 2 and 5 are both prime, so I'm done over there as well. When you write the prime factorization, it has to be in order from least to greatest. Let me say that again. When you write the prime factorization, it has to be in order from least to greatest. It will be wrong if it is not in order from least to greatest. It also has to be written as a multiplication statement because prime factorization is the product of its primes. So the correct answer here would be 2 times 3 times 3 times 5 times 7. Or you could write that with exponents. 2 times, instead of 3 times 3, we can write that as 3 squared times 5 times 7. And then if you were to type into your calculator 2 times 3 times 3 times 5 times 7, you would get 630. Okay, we've broken this down into the product of its primes. And so clearly 630 has way more than just two factors, so it is composite. All right, now you don't need to write this down, but I just want to show you, and in fact, I'm going to kind of do it over to the side here, and then I'm going to erase it because I'll need this space. But some of you might have thought, well, 630 breaks into things different than 63 and 10. And you're right, there's lots of things you could choose from. So let's choose something else. I could break it into 90 and 7. 90 times 7 is 630. Well, 90 breaks into 9 and 10. 9 breaks into 3 and 3. Both of those are prime, so I circle them. 10 breaks into 2 and 5. Those are both prime, so I circle them. And up here, 7 was prime, so I circle it. Well, what I want you to notice is that if you write that in order from least to greatest, you get the exact same thing. In other words, see here, you've got 2 times 3 times 3 times 5 times 7, which is what the same thing you got before. 2 times 3 times 3 times 5 times 7. So there is more than one correct way to do your factor tree. All right, let's do the next one together, 56. So again, you start by trying to think what is something that divides into 56. And there's several options, but the first one that comes to my mind is 7 and 8. So 7's prime, so I circle it. That branch is done. 8 can break into 4 and 2. 2's prime, so I circle it. 4 breaks into 2 and 2. Those are both prime, so I circle them. Remember, I need to go in order from least to greatest. So in this case, that's going to be 2 times 2 times 2 times 7. Or I can write it with exponents instead of 2 times 2 times 2. That can be 2 to the third power times 7. And unless the directions tell you, it doesn't matter if you write it with or without exponents. You can do it either way. And this is also composite. So right now we're going to pause the video and I want you to try the next one. Try to break 175 into its prime factorization, and in just a moment we'll press play so you can check your answer. Okay, so when you check your answer, your factor tree might look different than mine, but your answer should still be the same, and that is that the prime factorization is 5 times 5 times 7. Okay, so my guess is that some of you have seen this before. You have found the prime factorizations of numbers. What we're going to do next is we're going to start talking about something called monomials, which my guess is new for many of you, where we are going to try to factor things that have numbers and variables. All right, so we first need to define what a monomial is. Now, maybe you've heard the prefix mono. Mono means one. So a monomial is another way of saying one term. It is a number, a variable, or the product of a number and one or more variables raised to a whole number power. Okay, now that's kind of a mouthful, but try to write that down when it asks what is a monomial. It is a number, a variable, or the product of a number and one or more variables raised to a whole number power. So here's what this means. The number 10, that's a monomial. The variable x, that's a monomial. But it also can be the product, meaning the multiplication. So for example, 10x would also be a monomial. However, 10 plus x is not a monomial. And the reason that it's not is that that's combined with addition, but in order for it to be a monomial, it has to be a product. It has to be one term. 10 plus x would actually be two terms. It would be the one term 10 plus the other term x. Okay, let's try to identify a few more. It says label each of the following as a monomial or not a monomial. Number 1, we have 7x. This would be a monomial. The reason is we have the product of a number and a variable. Number 2, moving down, is 25mn squared. Well, we have a number, and we actually have two variables there, but that's okay. That is still a monomial. And again, the reason is it is the product of a number and one or more variables, in this case, two variables. Number 3, 7 plus x, is not a monomial because that is the sum of a number and a variable, not the product of a number and a variable. The last one, number 4, 24, y to the third power, z to the second power, would be a binomial. We have the product of a number, 24, and several variables there, all raised to whole number powers. Okay, so hopefully you have a little bit of a better sense what a monomial is. And now what we're going to do is we're going to factor monomials. Well, to factor something means to break it into its pieces. Okay, when we did the prime factorization, we were breaking it into its prime pieces. When we're factoring a monomial, we need to break it into all of the pieces that make it up. So if there's a number, you are going to write that number as the product of its primes. In other words, its prime factorization. And then the variables should be written with an exponent of 1. In other words, broken into all of its pieces. So let me give you a couple examples here. Number 1, I'm going to start by finding the prime factorization of 6, which 6 can break into 2 and 3. Those are both prime. So 6ab would be 2 times 3 times a times b. That's what it would be factored. That's what it is, broken into all of its pieces. Number 2, that 15 can break into 3 and 5. And again, 3 and 5 are both prime numbers, so I'm done with the prime factorization. So this would be 3 times 5 times n times n times n. I'm breaking that n to the third power into all of its pieces. It's like a repeated multiplication there. So it would be n times n times n. All right, on number 3, 3 is already a prime number, so I don't need to break that down further, but this would be 3 times x times x times x times y times y. Now, what you might be thinking right now is, why in the world are we doing this? Why are we trying to break something into its pieces? You're going to actually see in the next several days, we can use this skill of breaking something into its pieces to help us then find the greatest common factor and the least common multiple. So you've maybe found the greatest common factor and least common multiple of numbers. We're going to find the greatest common factor and the least common multiple of monomials. In other words, like, what do things with numbers and variables, what's the biggest thing they have in common, or what's their biggest factor, or what's the smallest multiple that they have in common. And by breaking it into its pieces, that's going to help us do that. So why don't you right now, we're going to pause the video, and I want you to try 4, 5, and 6. All right, go ahead and check your answers with mine. Again, I'm taking that number and I'm breaking it into its prime factorization, and I'm taking the variable parts and I'm breaking them into all their pieces, so writing it as repeated multiplication. And again, we're going to use this skill in the next couple days to help us with future problems. But right now, we're just breaking it into its pieces. All right, good work today. I hope you guys have an awesome day. And that's all we got for our lesson today.